So, today's concept, today's section, 1.1, working with parent functions and transformations. Now, today's concepts are things you have done before. You've worked with transformations before. In fact, if I recall, you almost spend an entire unit on it in algebra. So today we're going to be bringing back some of that information. Does anyone remember what a transformation of a graph is?
Just when you move over something?
And that's one option of a transformation. Moving it around, or really doing anything to kind of change up the graph. A transformation is when you change the size, the position, or the orientation of a graph. You make it bigger or smaller, move it up, down, left, right, or you flip it over something is essentially what those three things are. And we're going to get a little bit more into transformations, but before we get there, when it comes to our transformations, generally, not always, but a lot of the times, we're focusing in on moving around a parent function. At least that's what we're going to be doing today. Tomorrow we're going to start focusing in on transforming other functions. Do we recall what a parent function is of a graph? I know that more than one person in this room has a voice. I've heard them before. And if you don't remember, then you don't remember. Parent function is the most basic function in a family of functions. It is the function, it is the equation, it is the graph that is doing the least number of things but fits within a family. And families are really those different kinds of functions, the different kinds of equations. We deal with a lot of common families throughout high school. The one that we started in middle school was a linear family. So when it comes to the linear parent function, I'm just going to draw a little graph. Here's my XY axis. The linear parent function is the function f of x is equal to x. And it looks like this. Goes at a 45-degree angle from the bottom left to the top right. F of x is just a fancy way of saying what other item? Y. It's just a fancy version, essentially, of saying y. It's technically function notation. It works when we have functions. By definition, a function says that it is an equation in which each input has exactly one output. Every x I put into this will give me exactly one number out. It won't give me multiple numbers out of it. Linear equations, linear functions, are all technically functions. So, the most basic one, f of x is equal to x. Now, in general, what makes something linear is it can be written in the form of y equals mx plus b. where m and b are numbers. Y, aka f of x, and x are the only variables in there. Yesterday we talked about another family of functions. The one that it looked linear, but it was horizontal at all times. Constant function. We also have the constant family. Constant one is where you're going to have a situation where it's y equal to a number, or f of x is equal to just a plain number. Now for the constant functions, the parent function, yes, a horizontal line, specifically the horizontal line, f of x is equal to 1. There are 4 other families that you've worked with so far throughout high school math. You've worked with the absolute value family. If I take the absolute value of a number, what does absolute value do? Makes it positive no matter what. So, as a result, the absolute value function goes at a 45-degree angle that way and this way, because it takes those numbers and makes them positive. It is f of x is equal to absolute value, look like those vertical bars surrounding something. And I tend to make them a little bit darker just to emphasize that they are absolute values and not ones. Another family you've worked with that we will work with quite a bit in this trimester is the quadratic family. Quadratic family is the graphs that look like U's. The most basic quadratic function is f of x is equal to x squared. What makes something quadratic is that its biggest exponent is squared. And yes, it does have an exponent. Doesn't get bigger than 2, doesn't get smaller than 2. Biggest exponent is 2. It is squared. The last 2 families you've worked with is the square root family and the exponential family. Square root family starts at 0, 0 and kind of arcs off as you go to the right. It is f of x is equal to the square root of x. The exponential family starts just barely above the x-axis on the far left, and it kind of increases very quickly once you get past that y-axis. And its f of x is equal to 2 to the power of x. When it comes to an exponential function, what makes it exponential is the variable is in the exponent. Now you'll note I wrote down what makes something linear, what makes something constant, what makes something quadratic, what makes something exponential. I didn't write down what makes something absolute value, nor what makes something square root. What makes something absolute value? If you looked at an equation, you know it's absolute value because it has absolute value symbols in it. What makes something a square root function? It has square roots in it. That's why I didn't write those two down, because it has those symbols in it. What makes something quadratic, exponential, constant, and linear, those ones are not quite as straightforward. Now, with these various families, today we're going to be focusing in on the transformations with them. That changing of size, position, and orientation. Now, there are 3 different types of transformations that you can do to graphs. Transformations include translations, this is where you're moving the graph around. You can move it up, down, left, right, doesn't matter. You're just changing where it is. Still looks like the same thing, just not where it was originally located. There's reflections. It's where we flip the graph over a line. Specifically, we're going to focus on the x-axis or the y-axis. You can flip it over other lines, but it's going to make a very big difference on what you're doing when you do that. The last one is a word that doesn't get used very often. We generally skip over this word to talk about a little bit more specific of what it means, and it's a dilation. A dilation is generally where you are changing the size of something. But to be honest, yeah, we don't really use this word very often. Most of the time we skip over to, well, what do you mean by change the size? Generally speaking, we're talking about stretching it out or shrinking or compressing it down. Specifically in here, we're going to talk about vertical stretch or vertical shrink. At least today. We will be getting into horizontal stretch and shrink as well. You'll also hear me call a vertical shrink, or a horizontal shrink for that matter, you'll hear me refer to it as a compression. Now, how you do these to the different functions really just kind of depends upon what you do to its equation. So, we're going to just kind of start before we get back to actually writing some things down in our notes. I'm going to show you some graphs on Desmos. Now, those of you who've never had me before, generally speaking, during notes, if I do write anything up on the active board itself, or I do anything on the active board itself, it's not something I expect that you write down, unless I tell you otherwise. Generally, things you want to write down are things that I write down under the doc cam that just display up there. Apple TV reset my active board again. Yes, it went through all that work just to shut off. Do I try it again or do I pivot? I'm going to try it one more time because the Desmos is easier to kind of show what I'm doing on. If it doesn't work, then we'll pivot a little bit. Be able to speed up the process by simply unplugging it. It's not plugged in up there. Can't reach that. Anyway, I guess I'm going to show this to you on a calculator rather than on Desmos because I can't get the Apple TV to agree with me. Granted, I still need this to be able to do that, but I won't have to deal with it in a way that shuts it down. Okay, anyway, now that the graph hates it, or now that the computer hates it. Okay, so to kind of explore this a little bit, I'm going to start you off with one of the parent functions. If it's a U-shaped graph, which parent function am I starting with? Quadratic. So I'm going to start you with the quadratic parent function, and we're going to put some things in there just to kind of discover what it does. Now, you don't have to worry about too much about what I'm typing in and how I'm typing it in. That's not the point. The point is just to kind of explore the graphs and see what they do. So, currently I do have the graph y equals x squared in there. That is the quadratic parent function. So the blue graph is y equals x squared. It's good to know that. So I'm going to do some things to it. For example, I'm going to take x squared and I'm going to start doing some different operations with it. Adding, subtracting, multiplying, dividing type of thing. I'm going to add 1. The blue was the original, the red was the new graph. What appears to have happened to it? Moved up 1. Okay. If I add 5, what's it doing? Appears to have moved up. This time 5. What do you think is going to happen if I subtract instead? It's going to go downwards. There's the original. There is the one with the -5 on it. So it appears that adding and subtracting moves things up and down, right? But will it always move things up and down? In this situation, I added or subtracted after the x squared. Are there other places I can add or subtract numbers in an x squared function that is going to make a difference? And the answer is yes. I could add or subtract inside of the squared. Do it directly to the x before the function was actually put on it, before the squared was put on it. And if I do that, if I add 2, what did the graph do? Move to the left. Adding moved left. What do you think subtracting inside is going to do? Moves it to the right. So in general, adding and subtracting, regardless on if it's outside or inside, moves the graph around, performs a translation on the graph. There are other things that we can do to our graphs, though. There are 3 different types of transformations. There's translations, there's reflections, and there's dilations. What do you think is going to make something reflect? What do you think is going to make it flip over? Turning it into a negative instead of positive. And indeed, putting a negative in front of it flips it over the x-axis. But, just like with adding and subtracting, what if that's done inside? Now, it's kind of hard to see up on the active board, but did you see where the red graph ended up? In the exact same spot. Because squaring something automatically makes it positive. So is putting a negative inside the function appear to be doing anything? For quadratic, it doesn't appear so. But for now, let's take a step away from a quadratic. Let me put another one in here to look at, to explore that idea. So if I put the negative in front, we flipped it over. Now this is an exponential one. There was the original. There's the new. Flipped it over the x-axis. If I put the negative inside the function, in where the x is, does it do anything to the exponential? Yes. What did it do to go from the black graph to the purple graph? It flipped it where? Across what? The y-axis. It flips it left and right. Now, the question might be, now we already explored the positive and negative feature, but why do you think the graph of x squared flipping across the y-axis doesn't show it? Symmetric. Do you notice the left and the right of the graph look the exact same? So due to symmetry, you don't notice it here. But negatives will flip it over. The last option is the dilation. Stretching something out and shrinking it down happens when you put a number in front of it. If I put a 2 in front of it, vertically, did it stretch or shrink out? Vertically, it's a stretch. I know, most people look at this and they're like, what do you mean it's a stretch? It doesn't look like a stretch. It got skinnier. Vertically. Meaning, essentially, grabbing on to the very top ends of the blue, are you yanking it up or are you pushing it down? If this was a rubber band, if the blue was a rubber band, to make it skinnier, would I pull or would I give more slack in the rubber band? You would pull. That's why it's a stretch. It's because it's pulling it upwards. It's maybe a little easier to see. Oops, that's not what I wanted to do. Sometimes it's a little easier to see with like the exponential graphs, because there's the quadratic. The exponential one, you can kind of see it got pulled upwards a little bit more. That purple graph is higher than the black one. So it stretches out if I put a number in front of it, but only if that number is bigger than 1. If the number is smaller than 1, it's almost as if the rubber band got additional slack in it. It was compressed down. Vertically, someone put something on top of the graph and pushed it. Okay. So, we're going to take that information. Let's essentially summarize those things. Okay. When it comes to our transformations, specifically focused on the translations first. Moves up when adding to the function, and I'm just going to call it f of x rather than writing the function every time. And it moves down when subtracting. From f of x. Left and right had to happen inside whatever the function was. In other words, the adding and subtracting was specifically happening just to the variable x. Inside the f of x piece, inside whatever was happening to the x. Moves right when subtracting from x. Again, this has to happen inside of the function. When it came to the reflections, there were two different types. Flipping across the y-axis, flipping across the x-axis. It flipped across the x-axis, in other words, upside down. When the function f of x is negative. On the other hand, if you wanted to flip across the y-axis, that's when x was negative. Specifically, again, inside of the function. Went through a dilation. In other words, a stretch or a shrink. We're focused in on vertical for now. It is a vertical stretch when f of x is multiplied by a number bigger than 1. And last but not least, went through a vertical shrink, also known as a compression, when f of x is multiplied by a number between 0 and 1. One last quick note before we get to kind of the brass tacks, the basic, this is what you're going to be asked. When it comes to doing these transformations, order can matter on what the graph is going to look like. The proper order is starting closest to x and working outwards. I'll explain that a little more clearly when we actually get to the problems. Because today, the problems you're going to see are going to be very basic. They're going to ask you, what family does the function fit within? What are the transformations that are happening? Could also ask you to do a basic sketch. And note it says sketch, not graph, sketch. There's a difference between those two instructions. Graph, if I ask you to graph something, I'm looking for precision. I'm looking for accuracy. When I ask you to sketch something, I'm looking for the general gist of what it looks like. Now, you might not have all of these instructions in every single problem, but all of them work really nicely together. So I'm just going to kind of put the 3 instructions all together. I didn't mean to put a period there. So identify the family and its transformations, and sketch the graph as well as its parent. And you have to sketch the parent when you're doing a sketch of transformations, because otherwise you can't actually see the changes that you did. Oh my goodness, I'm getting ahead of myself. I'm going to start you with the problem. G of x is equal to 3. What are those symbols? Absolute value of x plus 2. What family is this in?
Absolute.
The absolute value family. Anything related to a number or a negative symbol is going to be a transformation that was put on the graph. Anything other than the parent, which a parent of an absolute value function is f of x is equal to the absolute value of x, anything additional to that is a transformation. So in this one, there are two different transformations that's happened. One with the 3, one with the 2. Start with the 3 because it's closest to the x. Between the 3 and the absolute value of x, would you agree that there's a multiply? Okay, so we multiplied by something. When you multiply by something, are you doing a translation, a reflection, or dilation? Which of these said multiply? Dilation. We multiplied by 3. Is that bigger than 1 or between 0 and 1? It's bigger than 1, which means we did a vertical stretch. Specifically, with a factor of 3. Okay, what does the plus 2 do to the graph? Since it's not inside with the x, it's being done to the entire absolute value of x, it is moving it up 2. If it was inside the absolute value, that would be either left or right, specifically left when it's plus. Okay, now we got that. We want a basic sketch of the graph. You want a sketch, you got to give me an xy axis. Notice, did I make it big? No, because it's a sketch. It doesn't have to be perfect. It doesn't have to be a big graph. I start with my very basic parent function. Absolute value parent functions look like what shape? Arrows with a V is V-shaped. Kind of going in at 45s if at all possible. So that's my parent function. F of x equals absolute value of x. Now, to do my transformations on it, I start with what was closest to the absolute value of x, and then I do the thing furthest away. In this case, the closest thing to absolute value of x was the 3, so I'm going to do that first. That's the vertical stretch. When I stretch a V out, again, it's like grabbing the very top of it and yanking it upwards. It is going to get skinnier. So it needs to get skinnier, and it also then needs to move up 2. So skinnier, I'm thinking this. Up 2 is going to be up here. That's my g of x function. And I don't have to actually write g of x equals 3 absolute value of x plus 2 because it's already over here. I did absolute value of absolute value. I did the f of x because it wasn't written in the problem already. That's the type of things you're going to see today, and not every question is going to ask for all of them. Some of them might just ask for part of that information. Some of them might give you the graph and ask for what happened, but they'll also give you the equation. Negative 2 to the power of the quantity x plus 1. First off, what family? Notice the variables in the exponent? Exponential. Transformations, you should start closest to x and work outwards. Now, granted, when you're listing them out, if you don't list them in that order, it's not the end of the world. When it comes to graphing them, you always want to start closest and then work outwards, otherwise it can mess things up. Okay, closest to the x is the plus 1. Adding 1, I know that's either left or up. If it's up here in the exponent, which is it? Did the plus 1 happen to the entire parent function or just to the x? Just to the x, which means that is the left and right. When it's adding, left. Moved left 1. Specifically translated left 1, but I'm assuming that left means one translation. Okay, the other thing that happened is I have a negative right here. A negative is a reflection, but is it across the x-axis or the y-axis? Did it happen to the entire function or just to the x? Entire function. That is x-axis flipping. Y-axis flipping is when the x itself is negative. So, flip or reflect, whichever you prefer, across x-axis. Parent exponential function looks something like this. Parent itself is f of x is equal to 2 to the x. I need to take this graph, I need to move it left 1. To figure out how to kind of move left 1, I recommend you just kind of find one point that's easy to work with on the graph, and then just kind of move to the leftish. Call that 1. And then do the other transformations with it. The other thing it needs to do is flip across. So I'm about this height above the x-axis, so I'll probably go about that height below the x-axis. And then because of that stretch, wait, no, it didn't have a stretch. Because of that flip, it almost looks like it's increasing faster, but it's not. Or in this case, decreasing. I have one more example to address one little hiccup that sometimes pops up. And we're not even necessarily going to graph this one for the sake of time. I just want to talk about one other thing that pops up. Y equals negative 1/3 x minus 7. What family? Linear. Can be written as y equals mx plus b. In fact, it is written as y equals mx plus b. There's two things that this sometimes messes with people on. First off, how many transformations are actually happening to this graph? 3. The 7 being subtracted, the 1/3, and the negative, those two are doing two different things. Start with the 1/3. A 1/3 being multiplied by the function is doing what to it? Vertical shrink. Now, I'm not going to be too worried about the factor right now, but in all actuality, a factor of a shrink is the reciprocal. We're going to focus more on that later this week, but in all technicality, this one's a factor of 3. Because the reciprocal of 1/3, the flipped version of it, is 3/1. What's the negative doing? It's a reflection across the x or the y axis. Here's the weird thing about this one. In a linear function, it's going to look like the exact same thing. It does not matter if you tell me if it flipped across the x or y axis for linear, it looks the same. Technically, we reference x-axis if you told me y-axis because it looks like that negative is being put directly onto the x, you're not wrong. -7. It's translation. What direction is it moving? I heard a couple different things. Being minus, it should either go to the right or it should go down. And with linear, those are also interchangeable. Because when you move a straight line to the right, the bottom part of it, kind of like if you think about this part moving right 7, the bottom part of it also essentially ends up looking like it goes down. That was a terrible explanation. My arm did not work in the way that I wanted it to. But technically, we generally think of linear moving up or down. But for a linear function, left or right and up and down movements will look interchangeable. So, doesn't matter.